All right, now that we've got our warm-up done, we are going to look at the chain rule. So this is the new stuff for section 3.6. And first off, what does it do? This allows us to take derivatives of composite functions. Okay, composites. Composite, there we go, composite functions. So stuff like we were just seeing in the warm-up, we don't have a rule for that yet. If we were told to take the derivative of sine x, like, sure, that would be fine. We did that in 3.5. But as soon as you make it the sine of square root of x, then we wouldn't really quite know what to do with it. So that's what the chain rule is for. All right, and there are a whole lot of things that can get written as composite functions, so this rule ends up coming up a lot, actually. And there's a couple different ways to look at the chain rule. It's different notations, different strategies here, and we'll go through all of them. They are all equally as good in my eyes. I have one that I kind of prefer for myself, but I want you guys to look at them and use whichever one is most comfy for you. So we'll start out with looking at the chain rule in Newton notation. This is our derivative notation with the primes there. So we're going to say that we have a composite function f of g of x. We could write it like the parentheses version as well, f of g of x there. Then the chain rule gives us the following for that derivative. If you're taking f of g, that's our function prime, so the derivative of f of g of x. All right, you would write it like this. F prime of g of x times g prime of x. That is the chain rule statement in Newton's notation. So just to look at what we're doing there to kind of break it down a little bit, what you're doing in this first part, that first multiplied factor there, is you're taking the derivative of f. Okay, so take derivative of f of x, well, which is our function that's kind of on the outside of the composite parentheses notation. So I often call that the outer function. So take derivative of the outer function, and you keep that same interior. So notice how g of x is still in there. We take f prime of g of x. So take derivative of the outer function, keeping your inside the same. Okay. And then you're going to multiply by the derivative of g. Okay, so multiply by the derivative of that inside function, because g of x is like your inside of the composition. So you multiply by the derivative of the inside function. Okay, so that's the first part, f prime of g of x here. And then there's that second part, multiplying by the derivative of the inside function. Okay, so that's one way of looking at it with Newton's notation. And then we'll get our other methods here, the Leibniz notation. So Leibniz, remember that's the derivative notation that's all like d dx, dy dx type of thing. So for setting this one up, we're going to say we have y, which is a function of u, and u is g of x. So u is a function of x. All right, let me write this down here, the whole f of u thing. Y is a function of u, but u is a function of x. U is a function of x. So it is getting that same type of nested composition effect. Y is a function of u is a function of something else. Okay. So the chain rule in this notation looks like this. The derivative of y with respect to x, dy dx, equals the derivative of y with respect to u, so dy du, times du dx, the derivative of u with respect to x. Okay. Now, some people like this way of writing the chain rule because it almost looks like these are little fractions here. They're not really fractions per se. The du, dx, dy, those things are actually little things called differentials, which we're going to look at in section 3.9. But it kind of looks here like the du's would cancel out, quote, quote, and so that's how you get dy dx. So that makes this notation kind of memorable here. But it is actually expressing the exact same thing as Newton's notation did. If we just rewrite it kind of in a Newton-y type of way, the dy du part, we are taking the derivative of y with respect to u. If y is f of u, that's just f prime of u right there. So this part is f prime of u because we're saying like y is f of u. And then du dx, well, u we're saying is g of x. So this is like g prime of x. Okay. G prime of x. But then if we do a little rewrite there, u right here, that is literally g of x. So that f prime of u is f prime of g of x times g prime of x. And so that is exactly the same thing that we had for the Newton notation. Okay. So yeah, that's all we're doing there. F prime of g of x times g prime of x. Okay, just in different notations. And then there's one more kind of method or approach to this. I call this the cover-up method, or sometimes I'll call it the hand method. And the idea here is not easy to write down. It's easier to just do it to a problem. So I'll demonstrate for you in just a little bit here. But the idea is you're going to cover up the inner portion of your function composition, take the derivative of the outer part, and then multiply by the derivative of whatever you were covering up. So that's the derivative of the inside portion. So we are going to end up with this still f prime of g of x, g prime of x type of setup. It just doesn't rely quite so much on notation. Okay, so speaking of examples, let's do some of those. That's like the whole rest of the packet, I think. All right, so lots of chain rule examples here. And we'll go through this first one and then pause for a moment to see how everyone is doing. So we are going to find the derivative of this function, find dy dx, and here we're starting out with a fairly basic type of function, y equals 3x plus 5 squared. And yeah, you could totally multiply this out, distribute, use the power rule. We're going to do it first with the chain rule, and then we can check it using the power rule, but we want to use our new toy here, so we'll do that. All right. So y equals 3x plus 5 squared. Okay, and I'm going to do this one in every notation for you, starting with Newton. Okay, so with the Newton notation, you are looking at a composition f of g of x. So g of x is on the inside, f is on the outside. So our g of x portion, the part you might see as being the inside of this function, is 3x plus 5. That's inside the parentheses. It's what's getting squared. That's our g of x. So g of x equals 3x plus 5. And then f of, let's say, maybe something else. No, I guess we would say f of x. That's your squaring function. So we're taking g of x here and we are squaring it. So squaring is what the f of x function does. So take whatever your input is and square it. All right. So now to get our derivative, we would want y prime. It's going to be f prime of g of x times g prime of x. Okay. So notice for this first part, you need the derivative of f. Okay, so f prime of x here, real quick little power rule, that's going to be 2x. Okay, so when we do f prime of g of x, we are going to take g of x and put it into the f prime function. So instead of x right there, we're going to put in g of x. We could even write that here like for this part, f prime of g of x, that would look like 2 and then g of x. Okay. And then times g prime of x. Okay. G prime of x here. Little power rule on that. That's just going to be 3. Okay. So there's g prime of x. And now let's put in the g of x function there. So we're going to have 2 g of x is 3x plus 5, and then times 3. And so when we clean that up just a hair, we end up getting 6 times 3x plus 5 for our final answer there. So that's the derivative of this function. Okay, so that's in Newton notation. Now for Mr. Leibniz. Leibniz. Okay, with the Leibniz notation, we have y equals f of u, and then u equals g of x. Okay, so y equals f of u. And then u equals g of x. Okay, so in that setup, u equals g of x, that's like the interior part of the function again. So it's actually going to be this g of x that we used in the Newton notation. It's the inner part, 3x plus 5. Okay. So now we're calling that bit u. And then y is f of u. So we're going to see what the f function does to that 3x plus 5 u there, that u function there. So it takes 3x plus 5 and squares it. So f of u is going to be u squared. Okay. And then let's take some derivatives of these because we're going to need them. We need dy du and du dx. So derivative of y with respect to u, that becomes kind of nice here because y is written in terms of u already. So we just get to use the power rule on that. And we say dy du is 2u. Okay. And then du dx, the function u is written here in terms of x. U equals 3x plus 5. So du dx is going to be 3. Okay. And so then dy dx is dy du times du dx. So we'd have 2u times 3. You could say that's 6u. But then to get everything back in terms of x, because that's how we want it, you would put in the fact that u, again, is 3x plus 5. So that would be 6 times 3x plus 5. Boom. Exactly the same as we got from Newton. All right. And now, one more. Let's do the power rule confirmation, and then I'll show you the cover-up method in just a second here. Okay, so power rule confirmation. All right, just to make sure that these other two methods turned out okay. So we've got y equals 3x plus 5 squared. And so we distribute that out. Remember to actually distribute everything like a full-on FOIL process. So that would be 9x squared and then plus 3x times 5, so plus 15x plus another 15x. That would be 30x and then plus 25. Okay, so that's just rewriting the function y. And then we could do dy dx with a nice little power rule on that. We would have 9 times 2x, okay, for the derivative of that first term, and then plus 30, derivative of 30x, and then derivative of 25 is 0, so that's all we end up with. So we get 18x plus 30, or if we factor it, we get 6 times 3x plus 5. Hey. Okay, so it is confirmed by using the power rule that this actually turned out okay. All right, sweet. Now it looks like I still have a little bit of space here. Let me show you the cover up method as best I can on here. Cover up. Okay. That way you get all your stuff in one place. Y equals 3x plus 5 squared. Okay. And I am going to utilize some pens here. Okay, to help with the covering up part. So description for this cover up method says cover up the inner portion of the function and take the derivative, then multiply by the derivative of whatever you were covering up. Okay, so to cover up the inner portion, we would want to cover 3x plus 5. I'm going to do it by drawing over it with a pen here because I can, because it'll erase real quick. But on your page, you might just want to cover that up with a hand or a finger or another piece of paper or something. Just cover, whoa, that was a lot of pen. Just cover that up. Okay. So basically, when we cover up the inside, we have purple block squared. Okay. And so when we take the derivative of that, we're just going to take the derivative of that like as if it were a normal thing to do, as if purple block there were our variable. You'd bring down your 2, doing power rule, and then you'd have your purple block to the first power. Okay, so let me even put purple block in there. Okay, 2 purple block to the first times the derivative of that purple block. Okay, boop, like that. 2 purple block, derivative of purple block. It sounds silly, but it can help once you get the hang of it. So then you would uncover whatever you were covering up. So just like erase that purple block if I can. Oop, it took out some of the other stuff. But when you uncover it, you see that, oh, that purple block was 3x plus 5. Okay, I'm going to recover that for the notes. But you put it back in here, 2 times 3x plus 5 times derivative of 3x plus 5. Okay? And then you'd have there 2 times 3x plus 5, and then derivative of 3x plus 5 again is just 3. And so that's how you end up again with the 6 times 3x plus 5 that hopefully we see is now the answer for surezies. Okay, so that is the cover-up method. So there's all 4 methods that we can use on this. Newton, Leibniz, cover-up, those are our chain rule in action, and then the power rule here was just to confirm that the chain rule actually worked. So I'm going to stop recording here for a sec, and then the next time we do recording here, I'll show you this cover-up method, but actually using my hand like I would normally show you like if we were in a classroom together. So let's pause for a moment.